Okay, good afternoon, everyone, and welcome to the first in a series of 7 webinars being presented by the National Corrugated Steel Pipe Association, NCSPA, in partnership with the American Galvanized Association, AGA. On today's webinar, we will be discussing the primary coatings available through current specifications from the members of the corrugated steel drainage industry and industry recommendations for how those coatings should be selected for use on various highway, rail, and other infrastructure projects. Future webinars will be hosted every 2 weeks at the same bat time, same bat channel of 2 p.m. Eastern on Thursday afternoons. Future topics will cover areas such as structural design and LRFD calculations, installation, water quality, sustainability, rehabilitation, and certification. PDHs and learning units will be offered and available for those participating this afternoon. So please be sure to complete your information and take advantage of this free opportunity. Membership of the NCSPA is comprised primarily of steel coil manufacturers and coaters and fabricators. The mills or manufacturers will produce and coat the steel sheet coil and ship it to the various fabricating companies that will in turn roll form, rivet, or fabricate the steel into pipe arches, and the various structural plate profiles, such as the boxes, single span arches, and multi-radius arches that are underneath our nation's highways today. These member companies will be participating and supporting our efforts throughout the production of this webinar series. My co-host for today's webinar is Scott Hensley with member company True North Steel out of Fargo, North Dakota. Scott is a Razorback, graduated from the University of Arkansas with a Bachelor of Science degree in petroleum geology. Scott has 30 years of extensive experience with corrugated steel drainage and buried bridge structures. Scott and I's focus today will be to show you all how coatings affect the service life of a product, and how a project application in specific environments can go a very long way to determining the best performing solution for a particular project. Now, there are three primary applications for corrugated steel drainage, or any pipe for that matter. The first two are culverts and storm drains. Now, the difference here primarily are culverts will carry the water from one end to the other, one side of the highway to the other. In this, you'll have varying degrees of bed load, whether that's velocity or size of the material rolling through. Whereas with storm drains, these are primarily running parallel to the road. You'll have minimum bed load. So these will have a smooth interior, low velocity, and these are used for primary collections and transfer of water. The third main application of corrugated steel pipe are detention and water quality installations. We will be covering this particular topic on the 4th webinar installment, which will be held on June 25th. The expectations or the desired service life of a particular project can be driven by a number of factors. The life of the pavement is a consideration. The traffic count, future expansion plans, and detour length can all be considerations when designing a project. Now, many DOTs have classified applications for a certain expected service life. Florida DOT is one of these examples. In Table 6.1 of their drainage manual, they differentiate between minor and major arterials, utilizing a service life of 50 or 100 years. And they also differentiate between side drain applications in both storm drain and cross drain, coinciding with culvert applications. Side drains and gutter drains, as you can see, have a 25-year service life recommendation. North Dakota is another example of differentiating the desired service life. They differentiate between mainline here, which is 75 years, an approach drain pipe, which is 40 years. And then finally, in Chapter 8 of their Highway Design Manual, New York State DOT, in Table 8.5, shows how the location will dictate the design life for their highway applications. So as you can see here, driveway culverts amount to a 20-year service life. Where significant locations, so those are defined below as under high fill or high traffic volumes, require a 70-year service life. Now, before I hand it over to Scott to talk in more detail about each of these coatings, I wanted to show you all a list of factors that could potentially have an effect on the durability of corrugated steel. These factors will play a part in determining which coating is recommended for a particular project, but we're going to pick that up later on in the presentation. Scott, take it away.
Thanks, Mike. Thanks again, everybody, for attending today. I guess I'll start off by saying the obvious, that you're going to see some things that may be new to some of you. Some of them you may be very familiar with, but coatings for corrugated steel pipe have advanced dramatically, and they continue to advance. As we research new coatings, new materials. But we'll focus on three of the more common coatings here today, and I hope you'll find this information informative. So I want to start off first of all and make sure you understand, and Mike mentioned it earlier, this is the raw material that corrugated metal pipe is made from, and it comes to fabricators like True North Steel or Lane, Comtech, Southeast Culvert in the form of coils, which you're looking at now. Those are individual coils of either galvanized or aluminized coating. We'll talk about what those coatings are here more as we go on, but that's the raw material that we receive to make the pipe out of. And at the end of my slide deck, you'll actually see a slide that shows the whole process, the coil, the machine making it, and the finished product. So I think it'll make more sense as we get to that slide. So first and most commonly used coating that has been around for forever, and literally 100 years plus, and used in corrugated metal pipe, is just a galvanized or zinc coated corrugated steel pipe. And it's just what it sounds like. It's a 2-ounce coating, and I'll show you how that coating is applied here in a minute. Been in use for over 100 years. It is what's called a cathodic protection system. The zinc, it's a different throw weight from iron or steel. So the zinc experiences metal loss before the steel, so it's a cathodic protection system, and that's how it works. You can see a sample of the corrugated metal pipe there with a stencil on it, and as you look down the pipe, you can see that stencil is repeated every few feet. So specifications for galvanized steel pipe, we have AASHTO specs, of course, and then married up with ASTM specs on this slide. M218, AASHTO M218 is the specification for the coil material, and M36 is the specification for the product itself. Flipping over to ASTM, same thing. You can see the related equal specs to the AASHTO specs there, A929 and A760. And then again, you can see on this galvanized coil in the middle, you can see the stencil that has all the pertinent information on it, the manufacturer, it's zinc 2-ounce coated, AASHTO and the ASTM spec, date it was manufactured, the heat number, and then the 16 at the bottom tells you it's 16 gauge. So as you can imagine, the process kind of in your head as to how you would coat steel. That picture on the right, those shows it starting on the left with a black steel coil that's heated, and literally goes through a molten bath of pure zinc. And in the center there, you can see a call out called an air knife. And it's actually air knives, and it's super fast air actually blowing on each side of that coil to smooth out the coating and make it nice and level and clean. And then it, of course, is coiled up on the other end as the finished coil that you saw on the first or second slide that I showed you. So specifications for the steel itself, you can see at the top there on the left, yield strength, a minimum of 33 KSI. We're pretty particular about the properties for what we call culvert coil, because we're going to turn this material, we're going to corrugate it, bend it. So it's got to be a pretty specific spec material for our use. In the middle, again, you can see the coating bath is 99% zinc. And at the bottom, and I hope you can see my pointer now at the bottom graph, that's from ASTM 929, and the top line is zinc. And again, it's a 2-ounce coating. You can measure that in terms of weight and what the thickness is as you measure using very specific test methods. So changing over from galvanized to aluminized steel, you're going to see some pictures and you're not going to be able to tell galvanized from aluminized steel. But once you become familiar with it and you see it in the field, you can see it is a different finish, a different color. And it is a completely different approach from galvanizing. Galvanizing, we talked about, was a cathodic protection system. And while there is some cathodic protection offered by the aluminum on the steel, its primary function is as a barrier coating. It's a barrier coating versus a cathodic protection. It's a 1-ounce coating. We'll talk about how that's applied in a minute. It's a very unique product that comes out. It forms an aluminum coating on the outside and aluminum iron alloy in the middle, and of course the core aluminum at the bottom. And of course, picture on the right is the finished product. It's been in use for over 60 years, and Mike's going to talk about some of the testing, ongoing testing that's been done. This product was rolled out very well originally by AK Steel, and they wanted to document how this product performed over time. So they did it right, started over 60 years documenting these installations and then periodically going back and inspecting them. So that's the stencil for it in the middle, same thing, AK Steel, Aluminized Type 2. 079 is the thickness instead of the gauge. But it's the date on there, 7/30/04, heat number, AASHTO, ASTM, same thing. It's a good time to mention here that as an industry, we source solely made in USA steel, because so much of our product goes to federally funded projects. Related specifications for aluminized steel Type 2, the coil itself M274, and M36 again, as with the galvanized coil. So I said a little bit earlier, aluminized is different, and it is different in the way that it's made. It's a much more I guess, complicated system than galvanizing. I'm not going to spend a lot of time talking about it. You can see it on that drawing on the right where it talks about the protective atmosphere that's different than hot dip galvanizing steel coil. That has to be that's very specific atmosphere for it to work. One of the main things that you need to understand about aluminized steel and what make it different from galvanizing, and Mike will talk about it in more depth as we go on, is that, as that first bullet said, unlike galvanizing or zinc, aluminum doesn't corrode in the presence of oxygen. That's a big difference. In fact, oxygen causes an aluminum oxide film to form on the exterior of the aluminum coating, and you can see that in real life if you've ever seen a brand new aluminum let's take a bass boat or something like that, and it's nice and shiny when you take it away from Bass Pro and stick it in the water, and you come back a year later and it's all kind of gray and waxy. That is the aluminum oxide that forms on the top of the aluminum, and it actually provides a very tenacious coating on the top of the aluminum, and that's part of the system that allows it to resist corrosion due to presence of oxygen, carbon dioxide, water, things like that, aggressive environmental conditions. So it's very unique and very different than galvanizing. Interestingly, and I'll show you here in a second, a cross-section micrographic photo on the next slide, but it's again unique because the steel and aluminum form a very hard aluminum steel alloy in between, and that looks like this on the right. If we went back and looked at the same microscopic photograph of the galvanizing and zinc, this layer is quite thin, and aluminum and steel in those right conditions form this big, thick layer in the middle. So it adds protection to the system in addition to just the pure aluminum coating. So, like I said, quite a bit different animal from galvanizing. Been in use extensively in the U.S. and actually around the world for 50, 60 years. So again, that's what this looks like, and it kind of gives you an idea of what the relative thicknesses are on the left for those different layers. So on to another different approach that diverges, dramatically from just plain galvanized coating and frankly from aluminized coating, and that's polymer coated steel. And it's just what it sounds like. It's a product where that same galvanized coil that you saw earlier in my slide deck, it has a polymer coating applied to it on both sides, and we'll look at how that happens and what the resulting product looks like here as we go on. But it forms a coating on both sides of a 10 mil polymeric coating, and it's applied using heat and pressure. And we'll look at that process here in detail in a second. But again, it forms a barrier coating that's it's resistant to virtually every naturally occurring environment. Makes it an ideal product for areas like where we work in North Dakota, in the western part of North Dakota, parts of Montana. The soils are extremely alkaline, pretty rough on a lot of different materials, and this is the ideal product. And North Dakota DOT has recognized that for years, that this is their preferred corrugated metal pipe go-to material because it will handle that super aggressive alkaline condition. So again, the specifications, the steel sheet again, N245, and the specs for the relating ASTM specs on the right. And the stencil, as you can see here on the top, it's a little bit blurred at the top. That it says Advanced Coil Industries at the top. There are 2 or 3 different coaters in the U.S. that apply this coating to the galvanized steel coil. Galvanized steel coil either comes from the mill straight to the coater, where they coat it, send it on to corrugated metal pipe fabricator, or a corrugated metal pipe fabricator could send them coil material from stock, coat it, send it back to them, turn it into pipe. So the ASTO spec for the coil, 246, it's a 2-ounce galvanized under it, and it's a 10-10 mil on both sides, was what the stencil calls out there. That was a copy slide, slipped in there somehow. Skip over that one. And this is microscopic cross-section of what that looks like, the 10 mil coating on the top, and then the zinc layer, and then the steel under. So this is just your basic galvanized coil under here. And again, this film it was originally developed by Dow Chemical, probably back in the 60s, 70s. It has been really the primary coating used in this polymer coated product for years. And if we go back sometimes and we look back to installations back in the 70s, and I mention this because we've seen some of it in Minnesota, they have coating, coated CSP test installations from the 70s that were called products like black clad, but 99.9% of everything you will see, even in the field going back and today, is got a trade name, trench coat, and that was Dow's trade name for the product. So busy slide here, but on the far left, we start off with those galvanized coils, and it goes through a process. I'm not going to worry about explaining what an accumulator is, but the coil is cleaned and scrubbed. When galvanized coil comes from the mill, if you don't call it out not to have it, it comes with a zinc chromate coating on it. It's kind of a waxy coating, so that coating, if it's on there, is scrubbed off in an acid bath, cleaned up, and then it's prime coated. The coating is applied under pressure, and then it goes through heater, sets it, goes out the other end, and you end up with a polymer coated coil over here on the right. So I told you earlier I was going to show you the whole process here. This is the coil. This, in case, is the polymeric coil going through the machine that actually corrugates the product. And this is what's called a lock seam die that creates that spiral lock seam that you'll see in the field if you look closely at any corrugated metal pipe that's spirally wound. We also, as an industry, in some areas still make what's called annular riveted pipe. It can be polymer, it can be aluminized, it can be galvanized as well, but this is a spiral machine. And interestingly enough, this is a slide from a manufacturer in Austria. Corrugated metal pipe is pretty much the same all over the world, whether it's in Russia, China, Australia, South America, Canada. It's the same product worldwide, same technology with some tweaks. But I just thought it was interesting. This could be a plant in the United States, but it's actually in Austria, and they use quite a bit of polymer coated product in Europe as well. So we've talked about corrugated metal pipe, and wanted to also mention that we, as an industry, manufacture a product called structural plate, and it's for larger structures. It's a different corrugation, and it comes in big sections that are bolted together in the field. But that product comes with galvanized coating, a hot dip galvanized coating, or it can come with a recently developed, you'll see the bottom bullet there, a polymer coated structural plate, not aluminized. It can't come in that product form, but it does come in galvanized, hot dip galvanized, and it is a thicker galvanized coating than standard corrugated metal pipe coil. And then, like I said, this more recently developed polymer coating on the structural plate accomplishes the same thing as the trench coat product. And lastly, going back in time a little bit as an industry, one of the initial attempts to extend the life of galvanized coatings was to apply asphaltic coatings, either hot dip galvanized or hot dipped with asphalt, or more recently spray applied. Most of that usage has switched over to polymer coated coil, the trench coat. You're looking at a structural plate picture here, and interestingly enough, that one's from China. I like to look at pictures and how things are done in different parts of the world, and they're still using it, an asphalt coating. And in fact, in many cases, in some parts of the world, we still have DOTs calling for a field applied spray coating on corrugated metal pipe, not structural plate. And we do structural plate as well, but a field-applied asphaltic coating primarily to the outside of large pipes to provide soil side protection. And again, that's primarily called out in places like I mentioned earlier in Montana, western North Dakota, where we have very aggressive alkaline soil conditions. So for the most part, when it's corrugated metal pipe, we should be using and specifying polymer coated product, but there are occasions when asphalt would be applied in the field primarily just for soil side protection. So I believe that's the end of my slide deck, and I'm going to turn it back over to you, Mike.
Everybody, now we're going to talk about coating performance. Now this particular slide, as you can see, isn't about performance, but is more about installation. But just to highlight another benefit of CSP, this is what will probably amount to a 40-foot length of pipe that's going to be installed as a culvert application. No joints, right? No joints to worry about. So on to coatings. How do we know as much as we know about CSP? Research has been going on this product for well over half a century. No pipe has been studied more in this regard. Now this picture illustrates the way two different coatings will perform essentially in the same environment, right? So you've got a galvanized material on the right-hand side, aluminized on the left-hand side. Clearly, the galvanized has suffered significantly through the life of this pipe. It's about 30 years old. But you know, at the end of the day, we know exactly why this happened. And the pH in this particular instance is why that particular pipe looked the way it did. So the pH in that particular instance was a little bit under 6, and the resistivity was around 2100. So pH and resistivity are two of the primary drivers of the service life and durability of these particular coatings. That's derived from the soil around it, the water that runs through it, the backfill above it, right? And what also percolates through that backfill. And then the abrasion levels are what obviously flows through the pipe. Flow velocity and bed load. Now, you know, without bed load, the velocity it doesn't really matter. It's the particles in the water that create the abrasion, right? So, chemistry lesson. What is pH, right? So pH is the measure of activity of a hydrogen ion in a solution that indicates the level of acidity, right? So how acidic is the environment, is the water? And then the resistivity. So resistivity is basically the inverse of conductivity in electrical current that can flow through the material. So these are the primary drivers for galvanized and aluminized anyway. Now, what we've done and what this chart illustrates are the minimum and maximum levels for each of the primary coatings as recommended. So as you can see here, galvanized, the min and max soil and water pH are 6 through 10. And the minimum and maximum resistivity is 2,000 to 8,000. Now, the maximum is really going to depend on whether or not you have soft water present. So we don't talk about this very much, but when soft water is present, it has a significantly deleterious effect on the galvanized, and aluminized would be certainly the required or in the recommended coating in that instance. So you can see aluminized here from 5 to 9 on the pH and a minimum of 1500. Polymer pretty much covers the spectrum on pH by virtue of its composition, and then resistivity. You know, anything above 250 is fine there. So now we can take this chart and we can reformat it just a little bit to illustrate those environments in a little bit different way. But again, this is really just to illustrate that this isn't just for the water moving through the pipe, that it is for the environment that it's installed in as well. Now this next slide adds two more variables to the equation, basically. The second column you can see here adds the estimated service life that we recommend for the given environmental conditions, both pH and resistivity. And then we've added the FHWA abrasion level category to the far right. And these are the maximum abrasion levels that we suggest these coatings be installed in. So now how are these coating levels defined, or abrasion levels defined? FHWA, oh, that slide didn't come through. So anyway, FHWA has 4 different levels, and they are derived from velocity and bed load. So a level 1 is, very low velocity, almost no bed load. Level 2 is I think up to 5 feet per second with a small amount of bed load. A level 3 is 5 to 15 feet per second with relatively granular small particle bed load, and then the level 4 would be something in the 15 feet per second above, and you've got some pretty significant sized boulders and rocks moving through it. So again, back to those recommendations for each of the coatings. The maximum recommendation for both galvanized and aluminized would be a level 2, and the maximum recommendation for polymer would be a level 3. So how does this relate to the application? So this is the previous slide. Culverts are going to have pretty high bed loads, pretty high velocities. Storm drains, pretty low velocities and not so much bed load. So that helps us in our decision process. So galvanized has been studied again for over 70 years probably now. Right, we're in 2020, and this research was done in the 1950s. So Caltrans studied over 7,000 installations back in the 1950s. These were primarily concentrated in the northwestern part of the state. Pretty mountainous terrain, so you saw some pretty moderate bed loads, heavy rainfall. So they were recording soil and water chemistries throughout the installation and throughout the performance of these particular installations. And what they came up with was service life definition is to first perforation of the metal. And that represented, in their estimation, approximately 12 to 13% of the overall metal loss within the pipe. Now, this is going to be primarily concentrated in the invert of the pipe. Typically, the soil corrosion is not a factor, but it's the invert that experiences most of the corrosion. So again, this is what they found is this was driven by pH and resistivity. So this is the bedstone of the calculations that everyone uses for service life for galvanized pipe. Now, AISI took a slightly different approach to the data, and you can see what this slide illustrates here is you have all of these lines, and then the curves are generated through this equation here. So this equation will help you plug in, and then you have gauge factors that, obviously, if you have a thicker gauge, you're going to see longer service life. So for this particular chart, 18 gauge was the base factor, and then as thickness goes up, the multiplier goes up. So 16 gauge would be a 1.3 multiplier on the service life predicted from this particular chart. So again, what AISI did is they looked at first perforation at 25% metal loss. So that's a longer time duration to get to your first perforation. And then what that results in is a slightly different equation where this multiplier moves from the 17 that you saw to the to 35. So that can have a significant impact on the depending on the environmental ranges. Now, aluminized. Aluminized has been studied pretty extensively in and of itself for about 50 years, almost 60 now. Initially, there were a couple of studies done by Federal Highways back in 91 and 2007 that looked at a number of installations around the country. Armco and AK had been doing somewhat parallel studies at 30, 43, and 50-year intervals to look at some other sites. These sites, amounted to probably 75 or 80 installations, and core samples were taken. That was the original evaluation protocol, is that core samples were drilled out of the invert of the pipe. Let's see this here in a little better in this next slide. So you can see this hole here that was drilled out. That was probably from the 43-year-old study, because this was the one that we did back at 50. So we're not doing this anymore, I think, is the long and the short of it. With the advent of ultrasonic thickness gauges and dry film thickness gauges, we don't need to do destructive testing on the pipe. That we can go in and there are even waterproof probes that you can stick in, and you can find what the coating thickness is on each of these without taking the coupon. And our most recent study drew the parallels to show that. And then you have polymer. Polymer, similarly, has been researched, again, for well over half a century. This most recent study, done in 2012, collects about 50 sites from 5 different states. The oldest site in this particular study was 38 years old. But you can see from some of the pictures there, these are in some pretty brackish waters, especially in Louisiana. The sites in Wisconsin are underwater mostly, in proximity to cranberry bogs and that sort of thing. So not the most benign of sites. And then the particular sites in New York are along up to Olympic Park, and it's a pretty mountainous terrain there, and pretty high flows, pretty aggressive and abrasive areas. So basically, the results of this study show that the polymer will add a 80-year add-on service life to the base galvanized steel beneath it. So how can I get more information on these products? Now, of course, state DOTs, again, they are the primary users of what we are supplying here. So back to Florida. So Florida has developed curves of its own. This particular curve is for aluminized steel, aluminized type 2 pipe. And as you can see, it's very similar to the pipe for galvanized developed by both Caltrans and AISI. So pH and resistivity are the primary drivers. And then you have your gauge factor here. So 16 gauge would be the base gauge. And then you can multiply it by 1.3 and 1.8 to get the service life for the other thicker gauges. Now, what does that result in? So, again, that results in shorter service lives and the lower pHs and lower resistivities. And then, high performing service lives, long service lives in the high resistivity, high pH regions. North Dakota, as we talked about them, they've done the same thing. So this is their corrosion tables. They've broken this out by abrasion as well. So, again, their most corrosive areas, they're not going to use galvanized. They're not going to use aluminized. They're required to use polymer, and that's what makes sense. Nebraska, similarly, a lot of polymers used in every application. Aluminized and galvanized can be used in some applications. There are some caveats, and those are mostly derived and driven by the environments they're installed in. The NCSPA has a plethora of online resources at your disposal. Our corrugated steel pipe design manual is the cornerstone of that. There's a wealth of information. Durability is chapter 8, I believe, in the corrugated steel pipe design manual. That's available for a free download from our website. course, we have the website, ncspa.org. We are going through a new release. We just migrated to a new site. So it's got a little bit of a new look and feel, but everything still is in pretty much the same place. If you want more information on projects for these particular coatings, under the newsroom, there's a Find a Project page. That's what shows this map here. So these are all projects that we've collected over the last 4 or 5 years for our Projects of the Year awards. So these are pretty high profile projects. But you can go in and you can search through these projects by coating, aluminized, galvanized, or polymer. You can search through by awards category. So we've broken that out into tension and retention system, structural plate, DOT categories, rehabilitation as a category, as well as Hall of Fame. So you can search by all of that. There are coatings pages for aluminized and polymer to give you some more detailed information, links to all the standards and specifications that Scott talked about earlier. Any videos that we have relating to the topic can all be found here. Finally, what I'm going to do is I'm going to walk through a couple of examples, some real life examples to show you how we would differentiate and how these products would perform differently in certain environments. So this first example I'm going to take is from a project that was in North Dakota. So it's a 75-year design life. It's a mainline application. Resistivity is pretty low. So 800, you had a relatively neutral to high pH at 8, not soft water present, and somewhat low abrasion level on the level 2. So when you hit calculate, so this is an area, this is in that green area, which covers most of the state. Now, after you calculate that, it'll present you a table of results. And you can see here that polymer coated would be the only product that you could install in this particular environment. So because the resistivity is so low and the desired service life is where it is, galvanized and aluminized just can't perform to that level in this particular environment. So polymer would be the recommendation. And this next particular example, so this came from Georgia, I believe. So 100-year service life. Resistivity is a little bit high, 6130, but the pH is low. So you've got a pH of 5. And what you'll see is, well, galvanized can work. It's a really heavy gauge. So aluminized becomes the solution of choice probably in that particular instance. You can get a 100-year service life with 14 gauge. That'll probably be the less costly option versus polymer, depending on the diameter. 18 gauge probably would not work. That's really only for small diameters. So anyway, our friends down in the southeast part of the country have done a lot of data collection on sites in that area. So in the North Georgia region, there are, I think they collected data on maybe 100 or so sites, all contained in this report that can be found on our website. And then finally, this came from a detention project in the western part of the country, Arizona, I believe. So they were looking at a desired service life around 65 years. Resistivity was low at around 1100, and then the pH was rather high, so 8.3, no abrasion. So what gets you there is 16 gauge galvanized. So even though it's a low pH or a low resistivity, the high pH becomes the driver. And if you go back and look at the equation, the pH, makes all the difference. Anything below a 7.3, and that would not be the case, but because it's 8.3 and because it's so high, that'll help drive the increased service life for this particular installation. So that's going to wrap up our webinar here for this afternoon. Of course, the next webinar is scheduled again for 2 weeks from now, May 28th at 2 o'clock. We're going to be covering structural design and LRFD calculations for that particular one. It'll be myself and a contact member presenting at that particular webinar. Please don't forget to sign up. Thank you again. Here's my contact information. We can open it up for questions. All right, so I'm looking in the chat room now, everybody. And let's see where I can find, let's see. Which is, from an economical and financial point of view, which is going to be the most appropriate? Yeah, so that's I mean that's the delicate juggle. So increased gauges, increased thickness will increase the cost. Polymer is more expensive than either galvanized or aluminized, but each of those coatings currently are about the same. Plus or minus a few percentage maybe. So it's yeah, I mean it's that's what the service life calculator is for. It's to show you what would be the lightest gauge coated that would meet your project specifications. So I hope that answers your question. Rolando, appreciate it. So the next question is, Amber polymer coated structural plate, what kind of protection is used for the bolts here? It would minimize damage occurring from the bolt tightening. Yeah, that's a good question. So there are a couple of different coatings available for the bolts. Performance varies with those different coatings. I would suggest that the user look at the specification A1113 to determine what would perform better. You can use polymer coated bolts. You could probably use galvanized bolts. It depends on again the environment and what you're using it for. All right. So the next question, Tim Pickering asks, what's the minimum cover for polymer coated pipe to have a long service life? Yeah, so we'll get into more of that in the next webinar, the structural design of it. But the minimum cover heights are not driven by the coating. It's driven by the steel itself. So 12 inches is typically the minimum cover for HL93 highway applications. In most cases, when you get into higher diameters, that does go up. But 12 inches is the minimum cover for most installations. Yes, the presentation will go out. The follow-up email will contain a link to the PDF of the presentation, and then we will also be posting the presentation and make it available on the NCSPA website as well. All right, so next question is how is polymer coating repaired in the field? So there's two primary ways to do that. The first and most common is just the paint. There's a liquid paint that can be applied, and that can be done at the plant or done in the field. Most nicks and scratches do not require a field touch-up. The specification now contains language where nicks and dents would not, but larger scratches would. So again, paint would be one option, and then there's a tape that's also available as well that might work for longer scratches and would be another option to do repair work. Thank you for your question, Philip. Any additional questions from the audience? All right. Well, thank you all for attending this afternoon. Hope you found it informational and worthwhile. And we hope to see you again here in a couple of weeks. Tell your friends, tell your coworkers, tell your bosses. Appreciate it. Thanks, everyone. Be safe. Have a nice day.